1 billion miles from home.
Antigo systems, Cassini,
running low on fuel.
We have a good lock.
Almost out of time.
We're putting down a fully functioning spacecraft.
After 13 years orbiting Saturn, the spacecraft Cassini is about to plunge to a fiery death, becoming part of the very planet it has been exploring.
Cassini was not so much of a mission as a way of life.
I've spent 20 years of my life on this. What we found was spectacular.
Cassini sent back dramatic visions of strange new worlds.
Nothing of what we had imagined came close to the reality.
It revealed methane lakes, electric dunes, buried oceans.
That moon has an ocean in it that could harbor life.
It's the end of a mission that has not only unveiled the beauty and probed the mysteries of Saturn, but has changed our view of the solar system forever.
Systems lead, mission planning.
Go ahead, mission planning.
The spacecraft has just crossed 30 degrees north latitude, altitude is 6,000 miles.
The dead of night, Friday the 15th of September. In the control room of NASA's Jet Propulsion Laboratory, the flight director and her team of engineers are presiding over the death of a spacecraft that they have nurtured for nearly 3 decades. In less than an hour, they will watch as Cassini sends its final transmission.
It's sad. It was 27 years of the investment of many lives into this.
Nearby at the California Institute of Technology is the vast family of scientists from around the world who run the 12 instruments on Cassini, measuring everything from infrared to radar, magnetic fields, and cosmic dust.
In some ways, I just want it to be over now. You know, you're sort of waiting for it to end, and it's really weird. Very mixed emotions at the moment. Really strange.
All have played a vital role in exploring Saturn. But it's Cassini's skills with a camera that have been truly inspirational. Head of the camera team and guardian of the Cassini Image Gallery is Carolyn Porco. Carolyn has been responsible for designing the camera systems, deciding when, where, and which pictures to take, and delivering and processing hundreds of thousands of images of Saturn, its rings, and moons.
This is one of my favorites. The reason why I love it is because we're seeing the rings edge on, and you just really can tell how thin they are. You can get the sense of three-dimensionality. And this is the famous hexagon, okay? This is the feature that drives everybody crazy because they don't expect to see something that is straight-sided in an atmosphere. It is nothing more than a jet stream, like our jet stream, okay? Really, you can relax. This is not the end of the world. Back at the rings, I mean, have you ever seen anything just so magnificently regular and beautiful?
With its 2 onboard cameras, Cassini has unveiled the Saturn system as a strange, mysterious, and unique place.
Saturn just captivates people because it looks so supernatural. It engenders the immediate feeling that it can't possibly be real. But we're lucky to have it. I think we're damn lucky to have Saturn. I'm glad I grew up in a solar system that had a planet like Saturn.
But taking and downloading such amazing pictures when your camera is 1 billion miles away through the bleak void of outer space is no easy feat. In charge of remotely managing the spacecraft from NASA's Jet Propulsion Laboratory is Julie Webster.
You know, scientists and engineers are true nerds, so you'll see a lot of nerd stuff on them.
Julie is Cassini's chief engineer. She's been caring for the Intrepid Explorer since before it left home and uses a scale model of the spacecraft to demonstrate its capabilities.
This is a quarter-size model, so this is a quarter-size me. I'd like to be this weight, not this height. So you start at the top. This is a 4-meter antenna. It was also designed for radar. So this is the composite infrared spectrophotometer. This is the ultraviolet spectrophotometer. This is the VIMS, visual and infrared. And these are the imaging cameras, the narrow angle and wide angle, that are used for the actual photos that you see. So this is the ion and neutral mass spectrometer that is the most important data that we're going to get in the last few hours. And here's part of the magnetometer instrument, and here's the other half of the magnetometer instrument. The trick is, the reason you want to put it out on a boom is you do not want to measure the magnetic field of the spacecraft. You want to measure the magnetic field of Saturn, or whatever you're at the time. Let's see. That's the nuclear battery. I actually sat inside this part during the build, so when I close my eyes and think of Cassini, I actually see the wiring inside the spacecraft and the things switching on and off. And when it goes in, that's what I'm going to see in my mind, is the aluminum melting on the structure. So now we're headed back up to the first floor, to my office.
Cassini divides its time between gathering data, which it stores on its internal memory, and then sending it back home.
A typical day, we're out taking pictures, collecting data, storing it on the solid-state recorder, and then we'll turn back to Earth and we'll play it back for 9 hours. We only have 4 gigabits of data that we can load up, and it takes 9+ hours to play that data back.
For 9 hours at a time, up to 6 times a week, Cassini sends its precious images of Saturn on a billion-mile journey back to Earth.
We have cleared the tower, and the Cassini spacecraft is on its way to Saturn.
So what does it take to get a spacecraft the size of a bus, with 12 delicate instruments, all the way to Saturn, and to keep it operating for 20 years?
And the solid rocket boosters have been jettisoned.
In the mission to get closer to Saturn than ever before, getting the Cassini spacecraft to its new home was a challenge for the team of fearless rocket scientists.
So, we'll go into the dark room.
Inside the dark room, the mission support area is where the whole flight team gathers for critical events, like the final plunge, launch, or orbit insertion. It took 7 years to get to Saturn, a spiraling journey that involved 4 gravity assists, close flybys past planets that boost the speed like a slingshot. It's a flight path designed by Head of Navigation, Dwayne Roth.
We had a Titan 4B.
Titan 4B.
So that was to get us away from the Earth, but then it still wasn't quite enough to make it all the way to Saturn. So we had 2 Venus flybys, gravity assist from each of those, an Earth gravity assist, and finally we got a Jupiter gravity assist, and that got us to Saturn.
Once Cassini was approaching Saturn, it had to perform possibly its most critical maneuver of the mission, a perfectly timed engine burn that would slow it down enough to be captured in orbit by the giant planet.
Saturn orbit insertion was obviously incredibly nerve-wracking. We spent 7 years guiding the spacecraft to get to Saturn, to get it into orbit. If it hadn't done the orbit insertion, which was a 90-minute burn on the main engine, if we hadn't done that, we'd have been a Saturn flyby and just gone on out in space.
The Doppler has flattened out.
During its 13-year stay, Cassini has revealed Saturn as a unique jewel in the solar system, a gas giant with swirling storms, a dancing sprinkling of moons, and surrounded by bright but paper-thin rings of ice. The origin of the rings is still a mystery, as is the complex gravitational interplay between rings, moons, and planet.
So this is one of those discoveries we made that really threw us for a loop. This is the outer edge of the B ring, and these, as you can see, are spiky shadows that are created by these features here that are sticking up 2.5 miles. 2.5 miles above a sheet of debris that's only 30 feet thick. It was just extraordinary. It was out of science fiction. That's what this whole mission has been.
But hidden in the images from Cassini are clues to the formation of this complex and dynamic system.
Well, we know the rings of Saturn are made of ice, and this is really solid block of ice here, but this is not the sort of ice the rings are made of.
Carl Murray is part of the imaging team, trying to work out how rings make moons, and moons make rings.
He sort of thinks it's more like sort of fluffy ice, so it's really the difference between a snowball and a hailstone. So this would be like a hailstone, but if you kind of break it up, you start to get more of a flavor for what the ring particles might actually be made of.
and the fluffy nature of the ice kickstarts the process of clumping.
So if the ice is fluffy, the particles perhaps are more likely to coalesce rather than to break up or bounce off each other, because there's more surface area for the particles to stick.
Eventually, gravity can take over, and a moon can be born. And it's the moons of Saturn, rather than the planet itself, that have offered up many of the most incredible surprises and mysteries to be solved. They're incredibly diverse, ranging in size from a few hundred feet to bigger than the planet Mercury.
But out of all these moons, the two standouts are Titan and then Enceladus.
Before Cassini's intrepid voyage, our best view of Titan was as an orange, foggy blob.
Titan was so mysterious to us before we got there.
At first sight, it may not look like much, but peer through the fog, and an astonishing world is revealed. A world that surprised everyone.
We hadn't let our imaginations go as wild as nature turned out to be.
On December 24th, 2004, Saturn's mysterious moon Titan began revealing its secrets to an eager audience when Cassini dropped a passenger, the European-built Huygens probe.
The Huygens deploy, we actually did that on Christmas Eve in here. It was the last year my father was alive, and this was a really important thing for him. And so he was able to sit up in the balcony and see his daughter say, you know, release the probe.
Huygens was designed as a descent module. Go through the atmosphere and tell us everything we can find out about this sister to our own atmosphere.
Planetologist Athena Cassinis has been with the mission since the beginning. And as Huygens fell through the orange atmosphere, she was at the European Space Agency's mission control in Germany, waiting anxiously for news from Huygens to find out if it survived the descent.
I remember telling my colleagues, please remove this image of Mars, this photograph of Mars here. We're waiting for Titan. And somebody said, it's Titan. And I said, no, it's Titan. We can see the pebbles on the ground. We can see the surface. And we're there, and the probe is taking images continuously of the same spot. The parachute goes right above, and so we can see the shadow of the parachute.
That was the first image they saw, but the best was yet to come. Huygens was busy gathering valuable data during the 2.5-hour descent through the orange gloom. These are actual images taken during the descent, joined into a seamless film, together with a recording made by Huygens of the sound of Titan's orange atmosphere.
And we started seeing channels carved through the hills, and we had this very dark area in the middle that eventually we identified as a dry lake. Nothing of what we had imagined came close to the reality.
Long after Huygens was tasting the atmosphere and snapping pictures of the surface, Cassini continued to explore Titan far above.
We went by Titan over 125 times.
Each flyby needs to be incredibly precise, and to prepare for them, Julie has a simulation of Cassini and the universe around it.
Hello.
The Integrated Test Laboratory.
A real-time, absolute time?
She uses the mock-up to anticipate every eventuality and rehearse every maneuver.
We must have run 10,000 simulations. When you fly spacecraft, you have to learn how to fly them. So the first 2 or 3 years were the most difficult, because you're kind of learning what makes the personality of the spacecraft.
Cassini was originally intended to orbit Saturn for just 4 years.
These are years by color.
But the mission has been so successful, it's been extended twice. By the end of the mission, it will have done a total of 293 orbits, covering every corner of the system.
Right?
Careful planning and endless simulations by Julie and her team kept Cassini in full working order, even after 20 years in space.
There's engineers and there's science, and we're the engineers. So scientists like to constantly be surprised, right? They like new data. They like to say, oh, I don't know what this means. I don't know what there's something new. Engineers do not like to be surprised.
And Cassini didn't disappoint the scientists. It delivered plenty of mystery and surprise.
These are dune fields, and the dunes are enormous. They're several kilometers apart. They're 100 meters high, and they go on and on for hundreds of kilometers. And in all these dark areas that you see, it's covered with dunes.
At first look, these dunes look remarkably like the very largest dunes found on Earth. But a more careful investigation reveals some very crucial differences. The sand on Titan's dunes doesn't blow in the prevailing wind. And the dunes seem to be resilient to all but the very strongest of storms. Joshua Mendez Harper and George McDonald have been trying to work out what's so special about Titan's sand.
One idea is that these dunes are cohesive or sticky, that the grains that make up these dunes somehow keep the dunes together. The question is, okay, if these dunes are sticky, what's causing them to be sticky?
On Earth, if you want to make sand sticky, you need to add water to help it clump together. But on Titan, the sand comes not from rocks or shellfish, but from Titan's exotic atmosphere.
Ultimately, it must be coming from the hydrogen and carbon that's stored in methane in the atmosphere. And so you're basically making sand from something that's raining out from the atmosphere.
Titan's sand is thought to be made up of hydrocarbons, similar in makeup to plastic. In their experiments, Josh and George compared Earth sand, which flows freely, with polystyrene beads standing in for Titan sand. And if your sand is made from something similar to polystyrene beads, it can easily build up a charge of static electricity, which makes it sticky.
So on Titan, when these winds blow, these hydrocarbon grains, particles rub against each other and charge frictionally. And so when you do that, things tend to clump together. The forces are strong. It does provide that stickiness.
Titan was already proving more mysterious than anyone imagined. Yet scientists were still searching for something that eluded them up till now. Surface liquid. One day, nearly 5 years after Huygens landed, one of Cassini's instruments spotted something shining through the haze.
That is basically the sun glinting off the sea of Kraken Mare.
Kraken Mare, the first alien sea ever discovered. And Cassini soon found a host of seas and lakes at Titan's North Pole.
I mean, this could be Earth.
Finally, Cassini had found the surface liquid that everyone was expecting.
In many ways, this lake is much like what we would find on Titan, but in other ways, it is very different. First of all, on Titan, the liquid is not water, it's liquid methane, because the temperatures are so cold that methane cannot be a gas, it's a liquid. The sky would not be blue, it would be kind of a deep orange.
Planetary scientist Janie Radebaugh is looking at the parallels between the two worlds.
The mountains surrounding this lake are made of rock, but on Titan, even though the mountains would look very similar, they wouldn't be quite as tall, but they would be heavily eroded, they'd have river channels, and they are made of water ice. And on Titan, ice is so cold that it is a solid rock.
Just as the Earth has a liquid cycle where water changes from clouds to rain to rivers, lakes, and seas, so Titan has one too, with methane taking the place of water.
This methane actually follows exactly the same cycle that water has on Earth, evaporating from the oceans, getting into the atmosphere, making clouds of methane on Titan, falling through the atmosphere in the form of rain of methane on Titan.
And with surface liquid, you find places with special significance. The meeting point between solid, gas, and liquid. A beach.
We're thinking more and more about the importance of beaches as a possible cradle for life on the Earth. What's so vital about a beach is you have this space where there is liquid interacting with solid materials, important building blocks, and the atmosphere. All three of those things can coexist on a beach. Those things together basically enable the right kind of chemistry, the right chemical conditions that may lead to life. Tons of larvae. Ugh, stinky.
Life on Titan's beaches is extremely unlikely, but it offers a window into some early pre-life processes on our own planet. Cassini Cassini and Huygens together lifted the veil of orange fog and revealed Titan's treasure trove of secrets, a moon strangely Earth-like and yet otherworldly. But it was another moon that would offer up the most delicious of discoveries, the tiny ice moon, Enceladus. The Cassini spacecraft's revelations about the ice moon Enceladus blew everyone away. They emerged initially from an unexpected source, from Cassini's sixth sense, its ability to sense magnetic fields. The magnetometer is an instrument run from London's Imperial College by Michelle Doherty.
This large boom here, which is 11 meters in length on the main spacecraft, is where we put our instrument.
The main objective of the magnetometer is to investigate the magnetic field generated by Saturn, to help probe the inner workings of the gas giant. For 20 years, data has been flowing from Cassini's magnetometer 1 billion miles away via the Jet Propulsion Laboratory into this small room in London.
Coming in the back is the direct link to JPL.
Early in 2005, a stream of data arrived through these cables that would radically change the entire mission.
In 2005, there were 3 planned flybys of Enceladus. The first flyby took place on 17th of February, and it was a distant flyby, 1,000 kilometers above the surface.
For the magnetometer team, this was a prospect no more exciting than any routine day's worth of data. But hidden in the graphs was the tiniest of glitches.
You can see there's a little pimple in the data, just over there, an anomalous signature. When I first looked at that data, I thought, oh, I know the spacecraft was moving really quickly. Maybe we haven't got the trajectory right. You know, maybe that's why we're seeing this funny signature in the data.
This strange signature seemed to suggest that something on or near Enceladus was somehow blocking the magnetic field of Saturn.
It's almost as if Enceladus is acting as a much bigger obstacle than its physical size. And one of the ways you can do that is if you've got an atmosphere. The other thing we noticed is there was a lot of noise in the data on either side, and what we were able to do is calculate what ions were generating those waves, and it was water group ions.
It seemed to suggest that there was some kind of atmosphere around the moon, an atmosphere of water that no one had anticipated being there. A second flyby a month later confirmed the results.
One of the reasons we waited for the second flyby is it was really weird to see that there was potentially an atmosphere on the first flyby, because Enceladus is small, and so the implication was there was something generating the atmosphere. So this was a real surprise. That's why I was so wary about saying anything until we had had the second flyby, just to make sure, because you know, you don't want to make a fool of yourself.
Michelle and her team decided it was time to alert the rest of the mission.
We knew for us to be able to have a chance of really seeing what was going on in Enceladus, we needed to get closer. And so we made the decision that I would go out to JPL and try and persuade the project to take us really close.
And so, armed with her anomalies, Michelle made the journey to JPL.
It took a lot of discussion. Not everyone was supportive. Some of the teams would then lose some data because some of the planned observations of Enceladus would have to change. But the project talked about it, and they then decided we would go much closer on the third flyby. And I must confess, I didn't sleep for 2 or 3 nights before that close flyby, because if we hadn't seen anything, no one would ever have believed anything I said again. So, but what we found was spectacular.
When Cassini returned to Enceladus in July 2005, it passed just over 100 miles from the moon. What it saw thrilled everyone.
We finally got to see the south pole of Enceladus, and here it is. It's crisscrossed by these major fractures.
Nicknamed the Tiger Stripes, Cassini found that these fractures were radiating heat.
Heat? I mean, who expected the south pole of Enceladus to be hot?
And what we found was instead of the atmosphere covering the entire surface, it was just focused at the South Pole.
And that's not all. Pouring out of the Tiger Stripes were giant geyser-like jets spewing water vapor and ice particles from the cracks in the ice crust. And the discovery of the plumes has revealed the origin of Saturn's outermost ring, a ghostly ring called the E-ring.
something like maybe 200 kilograms a second of predominantly water ice is thrown out into space. So what it does is form a ring, and that's the E-ring.
The question was, where was the water coming from?
We have been able to determine that there is a large water pocket or sea, deep sea, under the south pole of Enceladus. It's about the size of Lake Superior in North America.
Based on this discovery, many more visits to Enceladus were planned. The closest flyby was within just 16 miles of the surface.
And by the time we did that one, we were very confident.
So we flew in on thrusters because we didn't know what Enceladus would do to us, and then you were getting like one thruster pulse.
In the process of getting good at it, they used up all the propellant. They don't have much choice. But no, I think they've been very good at it for a long time. It's just that now some of these flybys are just exquisitely accurate.
So accurate and so close that Cassini was able to taste the spray. And what it found raised an extraordinary possibility.
This is now one of the places in the solar system where people think potentially life might have formed in the past or might be able to form.
I love this picture, and it's about as much meaning as you can get out of the Cassini mission, because we know that moon has an ocean in it that could harbor life.
If life evolved on that sealed ocean, then it must have evolved separately from life on our planet. It would be a sign of a second genesis.
I think that all we need to do is find that life has independently arisen just one other time. And that would tell us that it's everywhere. If it happened a second time, it probably has happened, a colossal number of times throughout the cosmos and throughout its history.
But sadly, ironically, it was this greatest discovery of Cassini's that ultimately sealed its fate. After 20 years, the great explorer is running out of fuel. And when the fuel is gone, so too is NASA's ability to steer the spacecraft.
We didn't want to lose control of Cassini and have it crash on the surface of Enceladus. If you discovered life there one day, there might be those doubters who would say, yes, but a spacecraft crash landed and took bacteria there.
And so the mission team decided to use the last drops of fuel to set Cassini on a final phase that would take it closer and closer to Saturn, before plunging into the planet and being destroyed, a phase NASA called the Grand Finale.
Systems, Cassini's station is currently looking for the X-band one-way carrier signal.
In April 2017, mission scientists gathered at NASA's JPL to witness the beginning of the end for the Cassini spacecraft.
There's a real buzz here of excitement and, slight nerves as well. The reason it's so exciting is this is the start of the end of the mission. We're running out of fuel, and we're going to make sure we go out with as much great science as we can.
The last phase of the mission, known as the Grand Finale, began with a hair-raising dive through the gap between the rings and the cloud tops of the planet. It's risky, but with the mission coming to an end, the team could afford to take risks that would previously have been unthinkable and send the spacecraft exploring closer to Saturn than ever before.
Everything looks great. We're just now waiting for the data.
It was worth the risk, because flying inside the rings will allow the team to explore enduring mysteries, such as the mass and the age of the rings, the exact length of Saturn's day, and in its final moments, the actual composition of the atmosphere.
And Go Systems, Cassini Ace, I can confirm science playback is in lock and starting to run.
The green spike was the first sign that Cassini survived the dive, and was now sending data back to Earth. The Grand Finale consists of 22 of these hair-raising dives between the rings and the planet before the final plunge into Saturn's atmosphere. From this unique vantage point, Cassini has already sent back these images from the atmosphere, taken on the very first dive, merged here into a slice of Saturn taken from closer than ever before. Analyzing images such as these will keep scientists busy for years. And this, the first ever series of images showing the rings from the inside looking out.
It's coming in right now.
Yeah, we are at about 2 hours before the plunge.
Critically, for those final moments of the mission, Julie must ensure that Cassini is able to collect and transmit data till its dying breath.
So what my team is doing right now is simulating the last 4 hours of Cassini's life. We've cleared off the solid-state recorders. We've dumped down all the pictures. All we're doing is as much real-time data as we can.
Data can only be sent as long as the antenna is pointing precisely at the Earth, something that will get increasingly difficult as Cassini starts to be buffeted by Saturn's atmosphere.
So what we do is we let the spacecraft go until it hits the 2 milliradian deadband, and then it fires a thruster to push it back, and then we let it drift over to the other side. It fires, so it's called bang-bang controlling. It doesn't know it's in trouble yet. Right now they're firing once every minute or so, and then as they get into the atmosphere, they'll start firing more and more and more and more in the last few minutes. And what we want to see is we want to see how much of the atmosphere we can see before we lose the signal, before it can't fight the atmosphere anymore and it goes off point. And then at that point it starts to burn up. It goes from 200 to 2,000 degrees in just a matter of seconds, and then everything will start to melt and disintegrate. And then it'll go away. We'll lose the signal, and that'll be end of mission. So pretty much everybody will know at the same time the end of mission, because we'll all see the carrier signal go away.
So after dedicating nearly 3 decades of your life to a spacecraft, how do you say goodbye? The Cassini-Huygens scientists and engineers have faithfully dedicated over 2 decades of their lives to the mission. And now, it's nearly time to say farewell to their beloved friend.
My navigation team will be sitting up here.
I will be out in Pasadena. I've spent 20 years of my life on this.
And back here, radio science is going to be one of the most critical positions, because they'll have the open loop receivers and they'll be the very last signal.
Cassini is going to be getting and transmitting data to its last breath. I'm going to cry my eyes out. I cried when it launched.
Everybody will be watching the spacecraft, making sure that we're getting all the data. This will have a cast of thousands. Every seat will be taken. Project manager, I usually like to sit next to Earl, so Earl will be here. I'm in the flight director seat.
Flight director systems lead, everything is nominal.
Copy.
Spacecraft has just crossed 10 degrees north latitude, altitude 1,000 miles.
In its final, fatal kiss,
We just had the transition to high rate mode, and we are in the atmosphere.
Cassini touched Saturn's atmosphere and then began to burn up, becoming part of the very planet it had got to know so well. At exactly 4:55 and 46 seconds Pacific time, on Friday, the 15th of September, the signal disappeared.
So that would be the end of the spacecraft.
Project manager off the net.
And Cassini, unquestionably one of our most successful missions into space, came to a final, spectacular end.
It's a 20-year-old friend. I can't imagine anything topping that, but we will try for a new mission.
It's always that way. It's like a death in the family, you know, it's imminent, but when it happens, it's the finality of it that really is what you're left with.
Cassini may be gone, but its revelations will continue. Results are already starting to emerge from the grand finale orbits. And we could be a step closer to discovering the length of Saturn's day by pinning down the mysterious tilt of its magnetic field.
If there is a tilt, it is really small, but we need to find that tilt if we're going to work out how long a day on Saturn is. I would think we would probably have a final answer in 3 to 6 months.
It's mission accomplished. And for us, it was a long, long mission. It was totally appropriate that it was slightly raining here as we walked out, because, you know, I think even the Earth is crying right now. That was a great spacecraft. It did exactly what we asked it to do, all the way to the end. No surprises.
And the legacy of Cassini looks set to continue long into the future.
Scientists will be poring over our images and all the data from Cassini for, I mean it, 100 years.
We've got this amazing amount of information to pass on to future generations.
We've only skimmed the surface of what's in that data.
Godspeed, you know, been a great spacecraft, a great program. You know, thank it and release it.
In its dying hours, Cassini left us with these final pictures. This is its last ever image.